Okay, wonderful. So I'm really pleased to be here today to talk about some of the work that we're doing in my lab on merging machine learning with classical dynamical systems and control. And before I jump in, I want to acknowledge many of my great co-authors and collaborators on these works. So this is only kind of a brief snapshot of the work that's happening in my lab and in my collaborative network, but I'm going to highlight a number of the work of these people today. So before jumping in, I do want to point out that if you are interested in any of these little vignettes or storylines, you can go check out more about this on my YouTube page, where we also highlight research papers from the group. And this is not just a shameless plug. I also want to point you to a new book that Nathan Kutz and I wrote on data-driven science and engineering. It has a strong focus on machine learning for dynamics and control. And you can download the whole free PDF here at the link below. Okay, so I like to show this movie of an eagle flying at the beginning of my talk because I think this really exemplifies a lot of what we are looking for in an advanced control system that leverages the modern data-driven and machine learning kind of revolutions. And so this eagle is able to seemingly effortlessly interact with an extremely complex three-dimensional unsteady flow field. And it does so with relatively limited sensing, so it doesn't measure the full three-dimensional flow field around it. To date, we have no evidence that the eagle knows about the Navier-Stokes equations. No these have ever been granted to eagle kind, but the eagle is still able to extremely robust control despite significant uncertainties and nonlinearity and high dimensionality. Now, some of the reasons we think this is possible, and I'm going to go into a little bit of philosophy before I start, is that we think that the eagle, so even though if we wanted to discretize this fluid in a computer, it would take us as humans millions or billions of degrees of freedom to describe that fluid. But out of those millions or billions of possible small eddies in the fluid, the eagle doesn't care about every single one of those. It cares about large, dominant, coherent structures on its wings that are responsible for lift and drag and agile turning. So the existence of these large-scale patterns in this fluid flow facilitate the eagle enacting a relatively efficient control scheme with reduced order models that just describe how those flow patterns evolve. And it doesn't need to measure everything. It can get away with just measurements of the local flow field on its wings and through its visual system. And so those are the kinds of things we're going to exploit for engineering control using machine learning. The existence of pattern facilitates kind of accurate and efficient modeling and control. Good. So when I go and talk to senior VPs at companies, oftentimes they see machine learning almost as like a magic wand. So they have a problem, an engineering problem, and they want to solve it with machine learning. And I think it's very important that we kind of demystify what is machine learning, because as engineers, it's actually, it's just a tool like all of the other optimization tools that we've had before it. And so in my kind of big umbrella view of machine learning, the way I see it is that machine learning is essentially an umbrella for modern data-driven optimization. Or said another way, it's how we build models from data using existing powerful optimization techniques, maybe on bigger computers. And so I think this is how we really should be thinking about it, is that we have a number of engineering tasks, dimensionality reduction, reduced order modeling, control, sensing. All of these engineering tasks, or most of them, can be posed as challenging optimization problems. So for example, control theory is firmly rooted in optimization. And in fact, most of the control problems that we solve on a daily basis are, for example, linear control problems, because that's where the most powerful optimization techniques exist. And we still have challenges in control when our system is high dimensional, nonlinear. Those give rise to non-convex cost functions that are very hard to solve using optimization techniques. And that's exactly where machine learning can come in, is that machine learning is extremely well suited for these high dimensional, nonlinear, non-convex optimization problems that come up in, for example, nonlinear control or control of a high dimensional networked dynamical system. And so that's kind of my perspective on how these two fit together, is that control is already an optimization constrained by the dynamics, and machine learning is a growing set of advanced optimization techniques for non-convex cost functions. Okay, good. So this is how I'm going to organize the talk. I'm going to just give a very high level view of a few vignettes or a few storylines of how machine learning could be used to model dynamical systems that we could then use inside of a controller. So we could kind of learn the dynamics from data, and I'll talk a little bit about what we do in my group in learning interpretable generalizable models. We can also learn the control law directly from experience, from trial and error, kind of how you would imagine an eagle might learn to fly. And so I'll talk about kind of the uses of optimization and machine learning for nonlinear control. And then another big part of what my lab works on is optimization for sensor and actuator placement. So using kind of the past data, past experience to optimize what sensors we use for future modeling, estimation, and control. And this is very much inspired by biology. In fact, flying insects have on the order of 100 strain-sensitive neurons on their wings. Fun fact, I didn't know until I moved to Seattle. And the insect uses those very few sparse strain sensors to detect what its wing is doing and what the surrounding flow environment is. And the insect can use that information to reject gust disturbances faster than the information can go up to its brain and back to its muscles. And so what that tells us is that this insect is doing local processing in its shoulder muscle to directly decide what action to take to handle those gust disturbances. And that's the kind of control performance we want. We want distributed sparse sensors, local computations that are fast, reflexive, reliable. Some combination of feed forward and feedback in these systems will allow us to handle time delays and large model uncertainties in kind of a model predictive control loop. Good. Okay, so I'm going to start with this dynamics vignette, and then I'm going to move on to the control vignette. So when I think of dynamical systems, my whole world is centered around dynamical systems like x dot equals f of x. And this is really what keeps us all in business, are these dynamical systems. And so a few of the key challenges we have today in kind of modern dynamical systems, one, and probably the biggest one, is that dynamics are often nonlinear. So we love linear control theory. We love linear dynamical systems because they're easy, because we can use linear algebra. There's one-line commands in Python and MATLAB to solve these systems. But most of the real world is nonlinear. Your pendulum very quickly becomes nonlinear when you try to swing it up, okay? And so a lot of modern data-driven dynamical systems or machine learning dynamical systems is centered around finding good coordinate systems or effective coordinate systems that simplify these dynamics. And often, sorry, my computer just crashed. Let me go back to my slides. Sorry, everyone. Okay, good. So modern machine learning dynamical systems is really focused on finding these coordinate systems that simplify your dynamics. And for us as control theorists, often what I mean by simplify is linearize. I want to take my nonlinear system and I want to look at it through some coordinate transformed lens so that it looks as linear as possible, and then I can recover my linear dynamical systems techniques. Another big challenge, and this one is not as often talked about, but it's a huge challenge, is that in modern systems of interest, our equations are often unknown or too complex to work with. So we're used to solving textbook control problems like swing up a pendulum on a cart, where you can write down Newton's laws or the Hamiltonian, and you can write down the equations of motion and start working with those. You can linearize. But what about if I want to control seizures in the brain, or a disease ripping across a continent, or the climate, where we either we can't agree on a model or we don't have models? That's the modern world we live in. Even in systems like turbulent fluids, where that eagle is flying, I have the governing equations, but they're far too complicated for me to work with in a control setting. So I needed to also discover reduced order models. And then kind of our approach to this, and there's a lot of groups in the world working on this. I would say, dozens, if not hundreds of groups working on these kind of two main challenges. What our group does is we put a premium on interpretable and generalizable models, models that are somehow physical by construction. If you know some prior physics like symmetries or constraints or conservation laws, we want to bake that into our machine learning process. And we also want to discover new physics in the process. Good. Okay, so I'm going to start by just zooming in really quickly to this dynamics or nonlinear issue. So one really exciting topic is Koopman dynamical systems. So a lot of you have heard of Koopman operator theory or the Koopman operator perspective of dynamical systems. And that's exactly what I was talking about. There exist these nonlinear coordinate systems where even strongly nonlinear dynamics will look linear. Finding those coordinate systems is extremely challenging. They might be arbitrarily complex functions to represent these coordinate transformations. But that's exactly what neural networks are good at, is representing these arbitrarily nasty functions. So this is work by Bethany Lush, who was a postdoc working with Nathan Kutz and me at the time, where she built a custom deep neural network autoencoder that had an additional constraint on the middle layer, that the dynamics in the middle layer had to be linear. So even for a nonlinear dynamical system, like a full nonlinear pendulum, she imposes this architecture that in the middle layer, the dynamics are linear. And in doing so, she learns this encoder map into that linearized coordinate system and a decoder map out of that linearized coordinate system. And in that yellow middle layer, you can do linear control theory, linear system identification. The dynamics are literally y dot equals k of y. And so we can use classical kind of easy one-line MATLAB and Python commands once we find that embedding into that yellow region. And I'll point out there's probably a dozen other groups that have worked on very similar Koopman autoencoders out there, and there's a lot of great work. Here's just a handful of those references. Okay, good. So, we have a whole avenue of work on finding these coordinate transformations from nonlinear to linear systems. Today, I'm going to spend more of my time talking about equation discovery, because that's something that's kind of new and exciting, that really is something our group is developing actively. And so, none of this is new. Model discovery is just a fancy new fangled way of saying system identification, which is something that we've been doing in our community for about 70 years now, right? So Ho and Kalman did system identification 60, 70 years ago. Okay, and now model discovery is just a new branding of system identification, except the difference here is that what we are discovering is a nonlinear dynamical systems model that has only a few terms or is parsimonious. It's as small as possible to describe the dynamics. And so what you get out is a model that you can write down and communicate with your friends and colleagues. And so that's why we call it model discovery, because we're not just building a black box that predicts, we're actually getting equations out. Okay, and this is relatively recent. There's been a big push in the last 10 years or so for this kind of parsimonious model discovery. So I'm going to tell you about our algorithm, which is the sparse identification of nonlinear dynamics, or SINDy as we call it. And I'm going to illustrate this on the Lorentz system. Now, why am I going into the data-driven discovery of dynamical systems? Because once we have these dynamical systems, we can do classical dynamics and control with those governing equations. We can linearize, we can develop controllers, we can do model predictive control. And I'm going to show you that in a little bit. So the sparse identification of nonlinear dynamics illustrated on this Lorentz system, imagine you collected a time series of the three variables x, y, and z that define the system. So those are the blue, red, and green columns on the right. And for now, let's say that you also have their time derivatives, x dot, y dot, and z dot. And I'm going to relax all of these assumptions later, but let's assume you measure everything. Now, we observe that the Lorentz system, the right-hand side equations on the left, are pretty sparse. Out of all of the possible functions we could have on the right-hand side, like sine of x times cosine y and things like that, these dynamics are pretty simple. There's only a few terms in each equation. And so that's why our SINDy algorithm starts off with sparsity. So what we do is we build a candidate library in gray here of this theta of x, of all of the possible functions that we think could be in our dynamics. So x squared, x cubed, y squared, y cubed, z, x, y, anything in this case up to fifth order polynomials, but you can pick any functions. And now what we're trying to do is we're trying to find the sparsest or the fewest columns of theta that add up to describe x dot, y dot, and z dot. And so this turns out to be a relatively standard sparse regression problem. So for example, I can find the fewest columns that add up to x dot. And in this case, we find that x and y nicely add up in a certain combination to describe x dot. I can do the same thing for y dot. We find that we need the x term, the y term, and the xz term. And the same thing for z dot. And in doing so, by applying this sparse regression, we discovered the structure of our nonlinear dynamical system. So here you can see the structure and the coefficients of our nonlinear dynamical system are identified. So this is true nonlinear system identification, but what you get out is a model that's interpretable, and it's as simple as necessary to describe the data. So we call that parsimonious. Okay, and so we're pretty excited about this. We've applied this to tons of systems and lasers, fluid flows, control systems, you name it, we've tried this out. And so we've done a lot with this algorithm. I'm going to show you some of the things. So I told you we measured x, y, and z and the time derivatives, but in most systems of interest, we don't actually measure the derivatives. We measure the state and we approximate or estimate the derivatives. So here I show that even if you just had these noisy state measurements, kind of these fuzzy white measurements, you could do a total variation regularized derivative and approximate the x dot, y dot, and z dot. And if you plug those into our SINDy algorithm, you would get a very good estimation of the structure of a nonlinear dynamical system and a pretty good estimate of the parameters. So this is just to show that you don't have to measure derivatives. We've also extended this to identify PDEs from data. So if I have this fluid flow past a cylinder, spatial temporal data, this is work by Sam Rudy when he was a PhD student with us. You can collect that data and you can compute partial derivatives, partial omega with respect to x, partial omega with respect to y, partial omega with respect to t, all of these partial derivatives and nonlinear functions. And you can build a similar library regression problem. And by applying sparse regression, just as we did with SINDy, you can identify the same dynamical system, the Navier-Stokes equations that actually generated the data. So this is pretty cool. If you gave me fluids data, I could run it through our algorithm and determine that the PDE governing that data was the Navier-Stokes equations. You can also do this with massively downsampled or subsampled data because there's so much spatial temporal data. Even if you zoomed into just a few patches where you could compute local derivatives, you could still estimate the Navier-Stokes equations. Okay, good. So if you're interested in this, if you want to try this out yourself, I just want to point out that we have open source code PySINDy that we just released on GitHub and in the Journal of Open Source Software. So check this out, download it, try it out for yourself. Okay, good. Now, we're talking about control today. So I want to go into kind of a little zoom in of how we've used SINDy for control problems. And this is work by Ulrike Kaiser, who is a fantastic postdoc working with Nathan Kutz and myself. And what Ulrike did was she took that SINDy architecture where you're trying to describe x dot as a sparse combination of candidate functions. But what she did was she extended that candidate library to not only include functions of the state x, but also functions of the control u. So here you can see that our library includes not just x, but also u and xu and u squared, nonlinear functions of the state and the control. And so I'll illustrate this on a predator-prey system. Those of you who are, apologies for the air traffic, those of you in the audience, I just would like to see if you can guess which predator-prey system I'm illustrating here. This is a fun cartoon. So if you apply so this is a predator-prey system where I am actively controlling one of the populations. I think in this case, I control the bunny population. And if you apply regular SINDy, you will learn a model that fits the training data very well because my control law was also a dynamical system. But then after the training period, after time 100, the SINDy model will start to diverge from the truth because it doesn't know what the control signal is. But when you tell the SINDy algorithm what the control signal u was, and you allow it to discover a model that has both the state and the control, even after the training period, the model has learned what the actual controller is. So long story short, you can discover the dynamics and the effect of the control, how it enters the dynamics in this way. And so this is just another way of kind of showing, you have your unknown dynamics, you collect your data with actuation U, you build your library, you perform your sparse regression, and you get a structural model out that also tells you how control enters. And so Ulrika has applied this to many systems, so population dynamics, chaos control, infectious disease, and flight control. And she's compared it against other leading methods like neural networks and dynamic mode decomposition. And all of her work, in this paper at least, is in the model predictive control framework. So the idea is we discover a model and then we use it for model predictive control. And because our model is sparse, because it has as few terms as necessary to describe the dynamics, but no more, it's very efficient. So you can use it very quickly for these future horizon forecasts in MPC. Okay, so we're using this MPC where you use the model, a short horizon model prediction to optimize the control. You take one step forward and you re-optimize, you take one step forward and you re-optimize, and you keep repeating this process. Very robust to nonlinearities. It allows you to impose limits on your actuation, hard limits on your state, things like that, inequality constraints. And so in SINDy with control, on the top in pink, you see the SINDy control. In the bottom, you see just a regular feed-forward neural network with control. And from left to right, we have an increasing amount of measurement noise on the system. And what you see is that even for relatively large amounts of noise, the SINDy model, the SINDy with control model, is able to identify the structural dynamics, which allows it to cope with noise much better than the neural network model. And so in this plot, we see that our SINDy model actually has a significantly better prediction horizon even than a big, beefy neural network that we trained on tons and tons of data. Because the SINDy model extracted the actual true sparse dynamical system, okay? And there's some benefits of doing that. It's more data efficient, for one. Okay, good. So I hope I've convinced you that you can use kind of sparse nonlinear model identification, the SINDy approach, for effective model predictive control in a number of examples. Okay, good. Now I'm going to go and tell you about another kind of cool thing you can do, which we call discrepancy modeling. And so the idea here is that instead of discovering your model from scratch, end to end, we often start off with a pretty good baseline model of our system. So we might have an idealized Lagrangian or know something about the symmetries or the constraints. And so if we start with an imperfect model, but we know that it's imperfect, we can focus our energy on modeling just the discrepancy term between measurements and our model, okay? So this is work with Koopman, and he here has built this really beautiful double pendulum on a cart in my lab. You can tell this is my lab because it's a little messy. On the top, you have the bad model. That's our imperfect, just a Hamiltonian model from a textbook derivation. But it doesn't take into account wind resistance, nonlinear bearing, chatter, and friction, things like that. The bottom model is once we have this discrepancy model kind of identified, you can do a much better job swinging up and stabilizing this control system. Okay, so that's the kind of thing you can do by focusing your modeling effort on the discrepancy. Now we're also applying this to advanced manufacturing for digital twins for like assembly lines and precision machining control, where you see that even though your simulation of this device is pretty accurate, over many, many arm motions, it might start to deviate from reality. And we want to have a discrepancy model to pin our digital twin to the real world. Okay, I think I'm going to skip this bit on parsimony, and I'm just going to jump right into kind of the next part. And this is the next big part of the talk, is how we use machine learning for control. So taking a big step back, we've talked about how machine learning can be used to identify and discover dynamical systems that can then be used for control. But what if we want to bypass that procedure entirely? And the example I talk about sometimes is, I think fluid flows are really illustrative of why we might want to bypass modeling entirely and just go to control. So in my field of flow control, fluid flow control, oftentimes what we do, and I've done this, basically my whole career, is you spend years painstakingly building a nonlinear dynamical systems model of your fluid flow that you're then going to use for control. Okay, and this is hard work because flows are high dimensional, nonlinear, they're tricky physics, okay? And once you've built that nonlinear model, you're going to develop a controller. And the minute you turn your controller on, you steer your system away from where you train that model to some new region where you might not have a very good handle on the physics. So long story short, the moral of this story is that you might not want to spend all of your energy painstakingly building a model just to turn on your control and steer your system away from that model. Now, if you're trying to stabilize a fixed point that you've characterized, that's a great time to build a model, because then your control is going to keep you near that model. But in lots of fluid applications, you're literally trying to push your system away from where your model was developed. That's the whole goal, is to decrease drag or change the lift, to change the flow. Okay, good. So I'm going to walk through a little bit of how we do this. And this is, a lot of this work is in collaboration with Bernd Nowak, who has been a long collaborator of mine in flow control, and we've developed a lot of this technology together. So fluid flow control in particular has just tremendous industrial applications. Almost every trillion-dollar industry, from transportation to energy to health to defense, has a working fluid at its heart. Okay, and so even a couple of percentage points of gain in flow control would result in huge kind of economic impact and technological impact. So again, we think of control as an optimization problem, and we think of machine learning as an optimization framework. So that's why these go together. So in this work with Bernd Nowak, what we've done is essentially try to learn effective nonlinear control laws using genetic programming. And I think this is a really cool idea that came out of his group, is that you can essentially take all of your sensors that you're measuring about your flow, and you can take all of the actuators you have, these U functions of what you can push on your flow, and you can start building these nonlinear functions from sensors to actuators. And at least in an experiment, you can generally try out a control law pretty quickly. Within 10, 20, 30 seconds, you know if your control law is working or not. So in a 10-hour day, you can try hundreds or thousands of these control laws. And using genetic programming or evolutionary algorithms, you can essentially take 100 initial controllers, try them all. You can rank the top 10% best ones, and you can kind of breed or mutate those into the next generation. Then you try all of those, and you take the top 10%, and you do the same thing generation after generation, and you essentially breed a better, tougher generation of flow controllers. And in lots of the examples we've tried this on in experiments, you're able to get extremely effective, high-performance flow control, reducing drag or increasing mixing above what you can do with kind of industry standard techniques. Okay, so another example I just love to showcase is this great work by Ben Strom, who is a PhD student working with Brian Palagi and me at University of Washington. And he was working with controlling cross-flow turbines. Okay, so a cross-flow turbine is essentially a vertical axis wind turbine if you knocked it over on its side and put it in a river. So that's what this picture on the left is, a river scale cross-flow turbine. And the movie on the right is a lab scale turbine that's in Brian's lab. So this one's not too big, maybe 1 to 2 feet in dimensions, or maybe half a meter in dimensions. And so with relatively simple data-driven optimization, which is what I call machine learning, Ben was able to get a 59% power increase over industry optimal control laws just by taking advantage of flow nonlinearities through this optimization. Okay, so I'll walk you through a little bit of what he did. What Ben did was essentially parameterize his control law. His controller gets to decide how fast do I accelerate and decelerate this turbine at different phases of rotation, because accelerating and decelerating gives you an effective angle of attack. It makes it look like your blades are pitching, even though they're not, because of the rotating frame. And so that is a continuous variable you get to optimize over, is the acceleration over phase angle. And so using a relatively simple in-loop simplex optimization from experimental measurement data, he was able to learn a control law that aligned the points of maximum torque with the points of maximum velocity, which gave them this massive green power bump you see in the right. So 59% increase of power just by learning good control laws here. Now, where this is going, our PhD student Isabel Scherl is working on putting these turbines in an array. So just like birds flock and fish school, we're going to be putting these turbines in densely packed arrays to pull the most power out as possible. And so we want to develop these coordinated control strategies for how these work together optimally. And again, you can think the parameter space for our optimization is just getting bigger and bigger and bigger, more high dimensional, more non-convex optimization. And so we're going to use a hybrid approach where we learn what the flow physics is from detailed measurements, from simulations, from models, and we're going to incorporate that into our machine learning control laws. So this is the experimentally measured wake behind one turbine, where you can see there's rich coherent structures, and we're going to use all of this information in a hybrid physics-informed machine learning control strategy. Okay, so another example I like to talk about, I think this is my last flow control example. Again, this is a high dimensional nonlinear dynamical system. If you don't care about fluid mechanics, you just substitute this for anything you do care about: the brain, the power grid, epidemiology, climate. These are all multi-scale, nonlinear, high dimensional dynamical systems. You know, I like fluids. In this case, this is work with Katarina Beeker and Sebastian Peitz from Paderborn, and working with Michael Delnitz and Nathan Kutz and myself. We essentially use a deep model predictive control network for advanced flow control. And so these are the two flow configurations. I have flow past one cylinder and flow past three cylinders, and we're going to try to control the drag and the lift in these configurations by spinning those cylinders. So this is kind of how the deep model predictive control works, is that to run the full Navier-Stokes fluid simulation would be far too slow for real-time optimization. That's on the left. So instead, we have a surrogate model. This is from our neural network. Our neural network is the surrogate model that we're going to use for much faster deep model predictive control. And so here, the task is to control or to regulate the lift coefficients on each of those three colored cylinders. So we have the light blue, the dark blue, and the yellow cylinders, and we're trying to get all of those lifts to track those reference lifts in the left plot. And on the right, we see the control performance. And we do a pretty good job. Just by rotating and spinning those cylinders a little bit, you can maintain very good control of those lift coefficients. Now, if you allow yourself, just like I was saying, we trained this model in one regime, and then we applied it and we changed the flow physics. So if you allow your model to adapt or to learn as it turns the controller on and moves off of this attractor that it was trained on, that's what I'm showing in the bottom, is that if you relearn the dynamics as you go, you can actually do a much better job tracking those references. You can see that there's a lot less variance in the lift coefficients, and my control cost goes down significantly. So we think this is really promising for lots of systems where when you turn on the control, you steer your system away from where it was trained. Okay, good. So that was a very high level overview of how, in my lab, we think of how to merge machine learning with control. So machine learning is just data-driven optimization modeling. And we can use that to develop models for control, MPC. We can use it to bypass modeling altogether and just learn effective controllers. And that's just a small range of the possible things you can do. So, you know, I hope you found this interesting. And if you have any questions, these are really the experts you should be asking. But I can stick around for a little while and try to answer any questions you have. Thank you so much. I really appreciate you being here and listening.
Yeah, thank you.